So we're going to build off what we know about motion with constant acceleration to talk about what is probably our most often used example for constant acceleration motion, and that's projectile motion. So where we're going to start is, hey, let's throw an object. So here's a ball, and what I'm going to do is I'm going to throw it across the room or whatever, and so there it goes. And so you can see here's the flight path of the ball, right there it traveled across the room. At some particular instant, I happen to have captured sort of the image of it here. And so at this particular instant, it has a velocity that points up in this direction. So I know the direction, I know the magnitude of the velocity, so I know the speed at which the ball is traveling at that instant. And so the question that I want to ask is, so when I throw that object, what factors influence how the object moves after I let it go? So why does it follow this particular flight path? Is basically the question we're asking. Well, I might be tempted to say that, well, how I throw it matters. And what I'm going to do is emphasize that we're only interested in after you let it go. Which means that clearly, if you've let it go already, there's no longer a force from your hand acting on the object, so I don't need to worry about that force. Well, I know once I've let it go, clearly gravity's still going to act on it. Right? My object still has mass, so gravity will still pull it down towards the Earth. And then I might be also tempted to say, well, if it's flying through the air, there's going to be some sort of air resistance or some sort of drag. And though this can be true for almost anything that you would throw like a ball, the air resistance is negligible. So what we're going to do is we're going to say we don't need to worry about air resistance unless we have a very special situation like a balloon. Right? A balloon clearly doesn't fly across the room the same way a ball does. But for almost anything else, air resistance is going to be negligible. We're not going to worry about it, which means that the only force that acts on our object after we let it go happens to be gravity. Well, what this does is it basically gives us a definition. So in introductory physics, a projectile, so when we talk about projectile motion, a projectile is defined to be an object whose motion is only influenced by gravity. So what this means is that for our course, when we talk about projectile motion, we're talking about a simplified model of what's going on that says the only thing that matters here is gravity. And for a lot of things, as we throw them across the room, throw them across space, that's a perfectly fine model. So that's the model that we're going to use. So projectiles, we only have to worry about gravity. Okay? Which means that the acceleration that acts on a projectile is simply due to gravitational acceleration. And I know that local gravitational acceleration always points downwards, which tells me that I know what the acceleration acting on my object does. It clearly just points straight down. So what this means is, notice I've got a coordinate system. So, and I happen to have made a choice of coordinate system where I'm letting the x be horizontal and the y be vertical. In this case, I've chosen positive y to be up, though again, we'll talk in a second about how I don't necessarily need to make that choice. But what we're going to do is say that for a projectile motion problem, since we know what's going on with the acceleration, the coordinate system we want to use for this problem is the one that takes advantage of the fact that the acceleration points straight down. So that lets us break up that acceleration vector into its x and y components, where if x is horizontal, well, then the x component of the acceleration is clearly 0, because the acceleration vector doesn't have a horizontal component. The y component, well, this is then all the magnitude of the acceleration. Since it's gravitational acceleration is 9.8 meters per second squared in our SI units. And again, notice I've got a plus or minus out here. So a couple things to emphasize. One is that g is a positively valued number. We're going to use g to mean the magnitude of the gravitational acceleration. So I know g is going to be positive. The sign here entirely depends on your choice in your coordinate system. Do you want positive y to point up, like what I've chosen here? If so, then I'm going to keep the minus sign. Because if positive y points up and the acceleration clearly points down, then I know it's pointing in the negative direction, so I need the minus sign. I could also, however, choose to let positive y point down. There's no reason I can't pick a coordinate system that says positive y points down, which means that then the acceleration would be pointing in the positive direction, and so I want the positive sign on in front of g. So again, you're going to be responsible for the plus and minus here, because it's really up to you to pick your coordinate system. Now, if what you choose to do is say, I'm always going to let positive y point up, then I'll always use the negative in front of g, that's perfectly fine. There's nothing wrong with that. But just be aware that, again, g itself is a positively valued number. The plus or minus, the minus sign that we often associate with g, is really about your choice of coordinate system. Okay. So what this means then is if these are the components of my acceleration, then this means that the x component, the horizontal component being 0, tells me that I have constant velocity motion in x. Right? There's no acceleration component, so what's going on horizontally won't change in terms of velocity. I do have a non-zero component for y, so my vertical component of the acceleration, it doesn't equal 0, so I know I'm going to have acceleration, but it has a constant value, so I have constant acceleration motion. So what we're going to see is the projectile motion, I will have constant velocity motion horizontally, and constant accelerated motion vertically. So let's see how that comes about. So again, I know what's going on with the acceleration acting on my projectile after I let it go. Fine. So what happens if, say, I drop something? So here I am standing on the top of a building, and I'm just going to drop something and let it go straight down. Well, if I drop it, I know that initially it doesn't have any velocity, so at the instant I let it go, it doesn't have any speed yet, but because the acceleration points down, it will accelerate downward, and it will travel faster and faster and faster as it falls. If, on the other hand, I threw something horizontally, well, again, this horizontal component is entirely in x. And we've already said that there is no horizontal component of my acceleration, which means this horizontal component of the velocity can't change. So as my object moves away from the building, when I throw it horizontally, what's going on in the x direction, again, x is my horizontal coordinate here, what's going on in the x direction, that doesn't change. So what this means is that when I throw whatever this object is, when I throw it horizontally, there are actually two pieces. There is the horizontal motion that stays the same, and there is the vertical motion that shows my constant acceleration. So as it moves over, now it has the same x component of the velocity as it did when I let it go, but now the y component of the velocity has increased because of the gravitational acceleration pulling the object down. As it goes even farther, again, x component doesn't change, y component gets larger. Goes even farther, x component doesn't change, y component gets larger. So what we see here is that what I've got is I've got a combination of motion with constant velocity in x. So again, constant velocity horizontally, and motion with constant acceleration in y. So constant accelerated motion vertically. Okay? So this is how we're going to deal with projectile motion problems. So there are a couple important things to sort of see from the picture. One is that if I want to talk about the speed, well, again, I know the speed is just the magnitude of the velocity vector, which means I need the x component squared plus the y component squared, take the square root, right? So when I Pythagorize my velocity vector to get the speed, notice that the farther it falls, the larger the y component is. The x component's the same in all these situations, so this term stays the same. This term gets bigger as the object falls, which means that the speed increases. And again, that's exactly what we know happens when you throw something. falls faster as it gets closer and closer and closer to the ground. The other thing, when I throw my object horizontally, notice that what happens is there's an angle that the velocity vector makes with the horizontal. Here, that angle wasn't very big. Here, it gets bigger. Here, it's bigger still. So that because the y component is increasing as my object falls, the y component of my velocity increases as the object falls, that the direction of the velocity makes a larger and larger angle with the horizontal as my object continues to fall down. So these are, again, we know how to deal with calculating the magnitude and direction of the velocity vector. These are just patterns that we see so that the speed's going to increase and the angle that the velocity makes with the horizontal is going to increase as our object falls back towards the Earth. Okay? So I could also choose, instead of throwing my object horizontally, I could launch it at some angle. So now I'm launching my object both out and up. So here's the initial velocity vector, the purple vector here. And notice it has both a x and y component. And I've drawn in the acceleration just to remind myself that, sure enough, it still points down. So I remember, of course, that a projectile motion problem is really just a kinematic problem where I know what the acceleration is. So I know the x component, the horizontal component of the acceleration is going to be 0. The vertical component of the acceleration, the y component, is going to be plus or minus g, depending on which choice I make for whether positive y points up or positive y points down. As my object now moves, again, I notice that x component stays the same because there is no horizontal component of the acceleration, but the y component decreases. It gets smaller until the point where the object reaches its highest point. So thing number one is that the highest point the object reaches is another way of saying that the y component of the velocity is 0. I saw that the y component of the velocity decreased as my object went up, and that's because the y component of the velocity points opposite the direction of the acceleration. So this component is going to get smaller and smaller and smaller because it points opposite the acceleration. The x component doesn't change. At the highest point, I know that the y component of the velocity equals 0. Again, we talked about how in some cases, or in some ways, this class is a foreign language course, right? We just have to know how these things translate. Here's one of the big ones with projectile motion. So when I tell you that the object's at the highest point, I'm giving you information that you got to know how to translate and get. Now, one of the mistakes that people often make is to think that at the highest point the acceleration is 0, and it's not. And again, we'll talk in class about how we know that the acceleration is not 0. Well, as my object starts to come back down, again, notice what I get is I get exactly the same behavior that I had when I initially threw my object horizontally on the last screen. So here I get an increasing y component as my object falls back down. The angle the velocity vector makes with the horizontal increases, right? So it points more and more downward because this velocity vector is getting larger. The x component of the velocity, again, it stays the same. So all these things I can summarize. I know that the y component of the velocity and the acceleration, they point in the same direction on the way down, which is exactly why my object speeds up. Right? This component gets larger because now the velocity and the acceleration are both point in the same direction in terms of the y component. I know that Vx is unchanged during my entire flight. Again, that's because there is no horizontal component of the acceleration. I know that, and then if I come back and look at sort of at the same height, so let's pick sort of this object, right, or when my object is right here and when it comes back to the same height here. So I know that Vx is the same horizontal component because that never changes. But if I look at the y component, here it points up, here it points down, but it's the same in magnitude. So the length of this component is the same. All I've done is I've flipped the sign. So the y component only changes its sign when the object is at the same height on the way back down as it was on the way up. So all I'm doing is saying, hey, here it points upward, here it points downward, but if it's at the same height, this y component has to have the same length. All I'm doing is changing the sign. Well, if all I do is change the sign, that means that x component of the velocity never changes. Y component of velocity, it changes sign but has the same magnitude. And since I'm squaring this term, whether it's positive or negative doesn't matter. So what this tells me is the object has the same speed when it's at the same height. So if it's at this height, traveling, let's say, with a speed of 10 meters per second, when it comes back down to that same height, it's also going to travel with 10 meters per second. Now the other thing that you can notice is the angle it makes with the horizontal at this height is the same as the angle it makes with the horizontal at that height on its way back down. Again, all I've done is change that here it's above the horizontal on its way up. Right? So the angle the velocity vector makes with the horizontal is above the horizontal on its way up. The angle the velocity vector makes with the horizontal is below the horizontal on its way down. So all these are patterns that we can see just from looking at what's going on with the components in projectile motion. All right, so we've got options. So I can take an object, I can drop it, it falls straight down. I can take an object, throw it horizontally. So it travels with some initial horizontal velocity, but then it has a increasing y component pointing downwards as it falls towards the earth. I can throw it from the ground so that it goes straight up and down. That's an option. I can throw it from the ground out at some angle. Right? I can also throw it from some height upwards. Right? So here I could stand at the top of a building and throw it straight up so it goes up to its maximum height and comes back down. I could stand on the top of a building, throw it up and out so that it travels up before starting to come back down. Or I could be over here, right, and start on the top of a building and throw it downward. So if I throw it straight down from the top of a building, that's sort of like starting the problem at this point. If I stand on the top of a building and throw it down and out, then that's like starting here. So you notice that basically what this image is giving us is sort of all the variations that we can kind of deal with, right? You can have, you can be at a height, throw it up to some point, throw it back to the same height, throw it straight up, throw it out and up. The biggest difference is that for this particular variation, it's really just a one-dimensional problem. I don't have to worry about anything going on horizontally because I'm throwing my object straight up. Here, I have two-dimensional motion. So this is a one-dimensional problem. This is a two-dimensional problem. That in and of itself is really about the only difference between what's going on. Everything else is just sort of changing the details about the direction you throw it, the speed you throw it, the angle you throw it. Those details don't sort of change the basics of how we work projectile motion problems. So you'll notice all of these are projectiles because in all of these cases, I know there is only the gravitational acceleration acting on the object. It points straight down. Given my choice of positive y being up, I need a negative sign in front of my 9.8 meters per second squared. So all of these situations are projectiles. It doesn't any of the variations we talked about. Now, here's one of the critically important things that students tend to make mistakes with. It's probably the biggest mistake students end up making when they're working projectile motion problems. So notice there are really three parts. When you read the problem, there's really three pieces of information that you're often going to get. One is going to tell you about what's going on at the launch. There's going to be what's going on in flight, and then it'll be, well, what's going on when it stops, right? So often if it hits the ground, let's say, if you throw it onto the top of a building or something like that. The important thing to remember is that for our projectile motion problems, the equations that we're going to use are only valid when our object is in flight. So we're going to use the information we're given at the launch to tell us the initial instant when gravity starts to be the only thing that acts on the object. And we're going to care about the final instant as being the instant just before it comes into contact with whatever it's going to hit at the other side. So one of the most common mistakes students will make is they'll say, oh, well, I'm interested when it hits the ground. When it hits the ground, it stops. And all that is true, but as soon as it comes into contact with the ground at all, now there's additional forces than just gravity acting on the object, so it's not a projectile motion problem anymore. So we're always going to be concerned with basically the right after, at the instant right after it was released, and the instant right before it stops. And that's again going to be a translation issue, because there's plenty of times where we're going to talk about what's going on when it hits the ground. And we've just got to be aware of the fact that when it hits the ground really means the instant right before it hits the ground. So that's going to be something that we're going to work on, and we're going to do some things in class to hopefully make sure that that comes across clearly. So our projectile motion problems are only when the object is in flight. So the launch piece, that's a different piece. Hitting the ground, that's a different piece. We just care about the in-between. That's what our projectile motion is.